Okay, good afternoon everyone. In previous class we started speed control of induction motor. Thus the speed of the rotor or induction motor n equal to ns 1 minus s. Here ns equal to 120 f by p and slip in terms of power p copper by p2. This is from the relation p2 is to p copper is to p mechanical equal to 1 is to s is to 1 minus s. So if you take these two terms, P2 by P copper equal to 1 minus S, 1 by S. So here S equal to just P copper by P2. So 3I2 square R2 by P2. This is slip in terms of resistance. So here to vary the speed of the induction motor, we can vary either frequency, supply frequency, or number of poles of stator, or rotor resistance. So if you change rotor resistance, we can change the slip S. If you change S, we can automatically change the speed of the induction motor. So these are the available methods. Another way of controlling the speed of induction motor is by changing input supply voltage. So in previous class already we discussed one method, that is cascade connection. Cascade connection of induction motor. For this we need to take two motors. Slip ring induction motor other one is squirrel cage. So cascade connection means the output of slip ring induction motor is given as input to the squirrel cage induction motor. This one is the shaft of the squirrel cage induction motor. So in this cascade connection, rotors are mounted in the same shaft. The rotors of this slip ring induction motor and squirrel cage induction motor are same. This one is squirrel cage. This is supplied by some 3-phase voltage source. So stator of slip ring induction motor is supplied by 3-phase voltage source. So due to induction principle, some EMF will be induced in the rotor, and here the motor is slip ring induction motor. So we have 3 slip rings. So from 3 slip rings we can take 3 wires, and this is given as the output of this rotor of this is rotor of slip ring induction motor. So output of the voltage induces in the rotor is given as input to the stator of this squirrel cage induction motor. This is cascade connection. Now number of poles of slip ring induction motor P1, number of poles of squirrel cage induction motor P2. Next, slip ring induction motor S1, and this one is S2. Next, synchronous speed of this motor NS1, and this motor NS2. Next, starter frequency. Starter induced EMF frequency is nothing but supply voltage frequency F. In this case, the starter induced EMF in the squirrel cage induction motor is the output of the rotor induced EMF of slip ring induction motor. So in this case, F1 equal to F, and in this case F2 equal to FR. So induced EMF in squirrel cage induction motor starter is nothing but induced EMF in the rotor of slip ring induction motor. So FR in terms of this F is S1 into F. So F2 equal to S1F. Here both the motors are mounted in the same shaft. So speed of rotors of both the induction motors are same N. So the expression for N in terms of slip and synchronous speed is N equal to NS1 into 1 minus S1. So in this case, N equal to NS2 into 1 minus S2. Here both the speeds are same because rotors are mounted in the same shaft. This is case 1 and case 2. If we apply same phase sequence, for both motors, it means here this slip ring induction motor has 3 terminals. Suppose these are the 3 terminals of this slip ring induction motor. This one is A, this one is B, this one is C. Supply phase sequence also A, B, and this one is C. So coming to this is for first induction motor, and coming to second induction motor. The output of this slip ring induction motor is connected to the starter of this squirrel cage induction motor. Here also we apply same phase sequence. This is from slip rings. This is from source. So here this one is A, this one is B, this one is C, this one is A, this one is B. Here both the starters. This is starter of squirrel cage induction motor, and this is starter of slip ring induction motor. Both the starters are supplied by same phase sequence ABC and ABC. If the phase sequence is same, suppose if you take ABC phase sequence, the RMF produced by starter winding, this is NS1, this is NS1, and this is NS2. RMF produced by starter winding of squirrel cage induction motor. This RMF rotates in clockwise direction, and this RMF also rotates in clockwise direction. This RMF also rotates in clockwise direction. If we apply same phase sequence, for suppose if the starter of squirrel cage induction motor is supplied by negative phase sequence, This one is A phase, this one is B phase, and this one is C phase of stator of spurious induction motor. But here this is A phase. This is from slip rings of slip ring induction motor B, C. Here this B phase is connected to this C phase, and this C phase is connected to B phase, and A phase is connected to A phase. Then in this case, the RMF produced in the stator winding rotates in anti-clockwise direction. But in the stator of slip ring induction motor, the RMF rotates in clockwise direction. This one is different phase sequence. For second motor. Then first case, both the motors are supplied with same phase sequence. Then ns1 into 1 minus s1 equal to ns2 into 1 minus s2. Next, coming to second case. So this ns1 rotates in clockwise direction, so 1 minus s1. Next, if we change the phase sequence, ns2 rotates in negative sequence. It means anti-clockwise direction, so it is represented by minus ns2 1 minus s2. Now the formula for ns1 is 2f by p1 1 minus s1 equal to, this one is ns2 means 2f2 by p2 1 minus s2. Here also 2f by p1 1 minus s1 equal to minus of ns2 is 2f2 p2 1 minus s2. Now f2 in terms of supply frequency is f2 equal to fr equal to nothing but s1 f 2 s1 f by p2 into 1 minus s2. This is 2f by t1 1 minus s1. 2f by t1 1 minus s1 equal to minus 2f2 is s1 f by p2 1 minus s2. Here 2f, this 2f cancel. Now remaining terms are 1 minus s1 by p1 equal to s1 into 1 minus s2 by p2. Here 2f cancel, so 1 minus s1 by t1 equal to minus of s1 by p2 into 1 minus s2. Now multiply with s1 minus s1 s2 by p2, and this one is s1 s2 1 minus s1 by p1. Here 1 minus s1 by p1 equal to minus s1 minus into minus plus s1 s2 by p2. Here product of s1 s2 is neglected. Because your slip means it will be nearly 0.02 or 0.3. S2 also assume some 0.01. If you multiply these two values, we get very small value. That's why we can neglect the product of S1 and S2. So 1 minus S1 by P1 equal to S1 by P2. Here also 1 minus S1 by P1 equal to minus S1 by P2. Now 1 minus S1 by S1 equal to P1 by P2. 1 minus S1 by S1 equal to minus P1 by P2. So 1 by S1 minus 1 equal to P1 by P2. 1 by S1 minus 1 equal to minus P1 by P2. Now 1 minus S1 equal to P1 by P2 plus 1. This is 1 by S1 equal to 1 minus P1 by P2. So if you apply LCM, 1 by S1 equal to P1 plus P2 by P2 and 1 by S1 equal to P2 minus P1 by P2. Therefore S1 equal to P2 by P1 1 plus P2, and in this case S1 equal to P2 by P2 minus P1. These are the slips in terms of number of poles in cascade connection. Now rotor speed. N equal to ns1 minus 1 minus s1. Here also rotor speed n equal to ns1 into 1 minus s1. In terms of first induction motor, it means slip ring induction motor n equal to ns1 into 1 minus s2. Now substitute s1 value 1 minus P2 by P1 plus P2 and n equal to ns1 into 1 minus s1 value is P2 by P2 1 minus 1. So ns1 value is 2f by P1. Take LCM. P1 plus P2 minus P2 by P1 plus P2. So 2f by P1, P2 minus P1 minus P2 by P2 minus P1. P2 cancel. Here in numerator we have P1 and denominator P1. This P1 this P1 cancel. Next here also P2 minus P2 0. This P1 cancel. So 2f by denominator P1 plus P2. This is n. Next in this case 2f. Here minus P1 in numerator and we have minus 1 because P2 minus P2 0. So minus P1 by P1, P1 cancel. So minus 1 by P2 minus P1 equal to 2f by P1 minus P2. So here speed n equal to 2f by P1 minus P2. So in cascade connection, we get speed of n equal to 2f by P1 plus P2 if the phase sequence is same for both the motors. Suppose if you want to decrease the speed further, we need to change the sequence of second motor starter supply. Then the formula for speed is n equal to 2f by P1 minus P2. In this case, speed is more. If you want to get more speed, then change the phase sequence of second motor. Suppose if you want to get less speed, same phase sequence is applied for both the motors. Then this denominator value increases, then the speed value decreases. This is for lower speeds and this is for higher speed. Suppose if you had to get a speed of synchronous speed of ns equal to 2f by p1, just connect slip ring induction motor and remove the constants of squirrel cage induction motor. Next, if you want to get the synchronous speed of 2f by p2, remove the connections of slip ring induction motor and direct connect the squirrel cage induction motor. So these are the four possible speeds in cascade connection. This is 1, this is 2, this is 3, and this is 4. Like this, we can get the variable speeds in cascade connection. Next, second method is rotor resistance method. So in rotor resistance method, we know the formula for slip in terms of powers, copper loss by P2. So 3I2 square R2 by P2. So slip is proportional to rotor resistance R2. If we add some resistance in slip ring induction motor, this is possible only, this rotor resistance control method is possible only in slip ring induction motor. So by adding some additional resistance, we can increase the slip. If you increase the slip value, if S value increases, speed of the motor decreases. Like this, we can control the speed of induction motor by changing the rotor resistance. Next, other method. Variable voltage and variable frequency method. So this method is called as VVR method. VV means variable voltage and variable VVF not R. This is variable voltage and this one is variable frequency. VV or V by F ratio control method. So as we know the formula for induced EMF in stator winding or rotor winding, some E equal to V equal to 4.44 F and this one is KW. KW is nothing but winding factor and means number of turns on stator winding or rotor winding. So if you want to get the voltage on stator winding, just replace N by N1 and KW by KW1. For rotor, by FR, this is number of turns N2, this is KW2. So here, if you observe this equation, this term is constant and number of turns also constant and winding factor also constant for a particular machine. Now, pi, this pi is directly proportional to V by F. Suppose in induction motor, if you want to change the speed of the induction motor, because Ns equal to 120 F by P, by changing the frequency, we can change the synchronous speed. But the disadvantage of changing frequency alone is, suppose if you increase the frequency to increase the synchronous speed, if F increases, what happens? Then flux decreases. But in induction machine, the flux must be constant. We need to maintain the flux constant. So to compensate the decreasing flux, the motor draws additional current, that is magnetizing current, IM. So the machine draws power current. So this winding may be damaged. So in order to overcome that problem, we need to maintain the flux must be constant. So this will be constant. Phi is constant. Suppose if you increase frequency, increase voltage also. Or other cases, if you want to decrease the frequency of decrease voltage also, then V by F is constant value. Suppose if V by F is constant, then flux is constant. Here flux is constant only whenever V by F is constant. Both the values are constant, then only the flux will be constant. Otherwise, if one value is kept constant, suppose if you kept V constant and if you change frequency, this flux value changes. And one more option is if you kept frequency constant and if you vary supply voltage, in this case also flux is variable. So to make the flux constant, we need to make this term constant. So to make this term constant, if you increase one variable, other variable also need to increase. For suppose if you apply 400 volts and 50 hertz supply, then here V by F ratio is 400 by 50. Then we get 80. Here V by F ratio is 8. Suppose here we want to change the speed of the induction motor. Then reduce the frequency to 25 hertz. So as we decrease the frequency to half, voltage also decrease by same factor. So this is also decreased by 50%. Then calculate V by F. V by F equal to 200 by 25. In this case also we get same value. So here in both the cases V by F is maintained constant to get the variable speeds by changing the supply frequency. So to get variable speed, we need to change the frequency. Along with the frequency, if you change supply voltage, the motor will not be damaged. The entire flux will be constant. So to make flux constant, we need to vary both the values. Both the values means voltage and frequency. Then only flux is constant. So this is the one of the method to obtain variable speeds in induction motor. Next topic, starting methods. Starting methods of induction motor. So in induction motor, the formula for current. So what is the purpose of starters? In DC machines, all of you discussed starters. Starters are used to reduce high starting currents. So here the purpose of starters is to reduce high starting current. So you know the formula for current, rotor current under running condition I2R equal to E2R by R2 square plus SX2 whole square. So this is SC2 by R2 square plus SX2 whole square. This is X2R.
Sir, root untademo కదా sir?
Okay. Root square under square root R2 square plus X2R whole square. This is the expression for rotor current. So at starting condition, S value equal to 1. then I2 equal to E2 by R2 square plus X2 whole square under square root. So under running condition, suppose if the machine is loaded, then slip value increases. Under running condition means S equal to ns minus n by ns. So under running condition, this value increases. The speed of the rotor increases, then the slip value decreases. If n increases, s value decreases. So if s decreases, E2 are equal to SE2 decreases. This as S decreases, this ETR decreases, then current I2R decreases. So under running condition, less amount of current flows through the rotor winding, but at starting condition, we have large amount of current through the rotor circuits and corresponding stator circuit. So because the relation between I1 and I2 is I1 by I2 equal to N2 by N1. So I1 equal to N2 by N1 I2. First, suppose if I2 is more, I1 is also more. It means at starting condition the machine draws more current, so it may damage the winding of the induction motor. So in order to protect the machine from high starting currents, we need to use starters. That is the purpose of starters in induction motors also. Same as DC machines. So we have different starters. First one is stator resistance starter. So in this method, a variable resistance is connected to the starter of induction motor. Suppose if the starter winding is star connected, and this one is the rotor. These are rotor conductors. This is a squirrel cage induction motor because conductors are short circuited by end rings. This one is TPST switch, 3-phase supply. So at the starting condition, these variable points are kept at these points. So if you kept at this point, the complete resistance is included in series with the each winding. Then there will be more voltage drop across the winding, and supply voltage to the stator winding is reduced. Suppose if the supply voltage to the stator winding is reduced, then current will be decreased. The starting current will be decreased due to reduced supply voltage. Next, under running condition, this rheostat is moved to this position. If the rheostat is moved to this position, this resistance, this variable point is moved to this position, then resistance is completely disconnected. So at starting condition, the variable point is moved to this position. At starting condition, this is a running condition. So in this method, reduced voltage is applied by changing the variable points at starting condition. So here the disadvantage of this method is due to resistance, there will be power loss across the three resistors, hence efficiency of the motor decreases. Next, here the resistance due to reduced voltage, the torque of the induction motor also decreases, because the expression for torque equal to Ks(E2) square Ks(E2) square R2 by R2 square plus Sx2 whole square. Here this value, this E value decreases due to decrease in E1. If E1 decreases, ET value decreases. If E2 decreases, the starting torque will be decreased due to this method. So these are the two disadvantages. So first disadvantage is high power loss. It means efficiency is less. Second disadvantage is less starting torque. But the advantage is we can reduce the starting currents due to introduction of this resistance at starting condition. Now coming to the formula for torque. So we know the formula for power. In terms of slip and copper loss. P2 is to P copper equal to 1 is to S. So P2 by P copper equal to 1 by S. Therefore P2 equal to P copper by slip S. So the formula for copper loss is 3I2 square R2. This is the formula for copper loss by slip S. But the expression for power in terms of torque is tau into angular velocity omega equal to 3I2 square R2 by S. So tau equal to we know the formula for I1 equal to N2 by N1 into I2. So here now I2 equal to N1 by N2 I1. Just here I2 is replaced by this term. Assume this is constant K and this is I1. So here I2 is replaced by Ki1. So Ki1 whole square R2 by omega into S. So here 3 value constant, K constant, this resistance R2 is constant. For a particular machine, R2 is a constant, this omega is also constant. So this torque is directly proportional to I1 square by S. Now if you want to find the full load torque, this is TF full load torque is proportional to IF means full load current, full load stator current. Here we represent in terms of stator currents. I1 is stator current. So IF square by SF. This is full load torque. Coming to starting torque. Before calculating starting torque, calculate starting current. Assume starting current of stator before using starter. Before using starter, the starting current of stator is ISC. Next, after using starter, so due to resistance, the current value decreases, because after using starter, the starting current is IST. Starting current IST equal to X times of ISC. So here X represents the fraction of reduced voltage. X is fraction of reduced voltage. So at starting condition, before using starter, take ISC equal to starting current before using starter, ISC equal to V1 by some Z. Now after introduction of resistance, the voltage is reduced to V1 is reduced to V2. So V2 is nothing but X times of E1. Suppose initially if you apply 100% means X equal to 1, then V2 equal to 1. Due to introduction of this resistance value, due to introduction of resistance value, or suppose V2 is reduced to V by 2, then X value here equal to 1 by 2. So before using starter, the initial voltage is assumed as 100 volts. Then after introduction of starter, the supply voltage is reduced to 50 volts. Assume this one is V2 and this one is V1. Now V2 equal to 100 by 2. Here 100, 1 by 2 into 100. Here 100 is nothing but V1. So this 1 by 2 is the fraction of the reduced voltage. So take it as X. So V2 equal to X into V1. So V2 means voltage after introduction of starter, and V1 is voltage before introduction of starter. Now starting current after introduction of starter, this is IST, means after using starter, starting current IST equal to, IST is nothing but V2 by Z, but V2 in terms of V1 is X V1 by Z. Now initially before using starter, V1 by Z is nothing but ISC. So here IST equal to X times of ISC. IST means starting current after using starter, and excess is nothing but starting current before using starter. Before using starter, ISC is starting current, and after using starter, starting current is IST, and the relation between these two currents before using starter and after using starter is IST equal to XISC. I think it is clear to everyone. If you have doubts, I will repeat again. Is it clear?
No, sir.
Okay. Now IST equal to XSC. Now starting torque. This is starting current after using starter. Starting torque after using starter. So torque proportional to I1 square by S. At starting condition, S equal to 1. So starting torque TST proportional to IST whole square. So here S equal to 1. So TST proportional to IST whole square. This is starting current. IST means starting current after using starter. So starting current after using starter in terms of starting current before using starter is IST equal to XISC. So replace IST by XISC. This is whole square. Now this is equation 2. So equation 1 is full load torque is proportional to full load current square by full load slip SF. This is equation 1. Now divide equation 2 by equation 1. Then we get starting torque by full load torque equal to XISC whole square by the expression for full load torque. Full load torque is IF whole square by SF. So IF whole square by SF, which is equal to so starting torque equal to this is x square ISC by IF whole square into SF, full load slip SF. So due to introduction of starter, this resistive starter, the starting torque is reduced by x square times of this full load torque, x square times of this full load torque, and this can be represented in terms of per unit value. So per unit value of starting torque, per unit value of starting torque. So per unit value is nothing but actual per unit value means PU, per unit value equal to actual value by base value. Suppose if you want to represent 2000 in terms of kilo. So 1 k equal to 1000. So 2000 by 1000. Then we get this is 2k. This is actual value. Here we take base value as 1000. So this is nothing but 2k. 2k per unit value. So here just this is the one example. So here this starting torque is represented in terms of full load torque. Here this full load torque is base value and this one is actual value. So this is the per unit value of starting torque. So this entire value TS to be TF is taken as the per unit value of starting torque equal to x square into this is ISC by IF is nothing but per unit value of starting current. Per unit value of starting current whole square into SF. This is in terms of per unit values. So generally this is not necessary, but it will be useful in gate bits. Is it clear? If you have any doubts, ask me. Otherwise, we can leave. Again, we will meet on Monday.